So now we have to actually use these similarity values, and before we do that, we have to calculate the similarity values. And when we actually do the similarities, we do them on the errors that we obtained in the baseline prediction. So we basically subtract out to figure out how off the baseline prediction was, just for the training set again, because we can only use the training set. And then we augment the baseline predictor with the similarity values that we obtain on the errors. And so there's a couple reasons why we do that. First is that we really need to center these values at 0. And the reason they're centered at 0 is that we're kind of subtracting any bias out already by the fact that we're going to an error. So the errors are going to include 0, and in a sense they'll be centered around 0. And in order to do correlation, you need things to be centered about 0, so then you can either have positive or negative values. So if we did them on the ratings themselves, which are from 1 to 5, we can never have negative values. We'd only have positives, and that doesn't give us that sign differential that we need. So we subtract out, and we do them from kind of around 0 to some positives and negatives. And the second reason is that we're trying to correct for the errors here, right? So this is an augmenting the baseline predictor with this similarity, the neighborhood method, really, it's called. And so we want to correct for those errors, so we really don't want to do it on the errors themselves, because that's what we want to sort of to go away. And I mean, we're not just going to add the errors back and give us 0 error and everything. We're going to do it in a way that makes sense and is not quote-unquote reverse engineering. We'll see how we do that in a minute, but first let's try to calculate some of the values. So here I'm showing the table that is, so here I'm showing the table of error values, and I got this by subtracting the predictions from the actual values. So I took the actual values and I subtracted the predictions. So if the predictions were higher than the actual values, then this is going to be negative, which means, well, we should have made the prediction lower than we had it. And if the predictions are less than the actual values, then this will be positive, which means the prediction should have been higher. And so we can use the positives and negative values accordingly. But now for movies 1 and 2, let's just apply that cosine similarity. To do that, we have to just figure out now the users that have rated both movies, because we can't use, in the equation, we can't have users that have only rated one, and clearly we can't use those that have rated none of the movies. But for instance, we can't use A here because A has not rated movie 2. We can use B. We're good because B has rated both movies. We can't use C because, well, this is part of the test set again, so we can't use the test set. We can't use D because this is part of the test set. We can't use E because we don't know this value, but we can use F because we know both of these. So we have to use only B and F for this. So for movies 1 and 2, then we're just going to apply that equation that we had before. We multiply B1 times F1, so we do negative 0.30 times negative 0.05. And then remember, we add, so we add the product of the terms. So we do this times this plus this times this. So then we add 0.17 times negative 0.58. And then remember, we have to divide by the length. And then we divide by b square root of b1 squared plus b2 squared. So this is negative 0.3 squared plus 0.17 squared. And then we multiply that by negative 0.05 squared plus negative 0.58 squared. Then if we do this out, we get negative 0.0220 over 0.3041 times 0.6044. Right, so this whole top right here comes to this comes to this, and this comes to this. And then that is equal to negative 0.11. Okay, so the cosine, or the similarity between movies 1 and 2, is negative 0.11. Remember, now we said that we have to see whether it's close to -1, 0, or +1. And if it's closer to -1 or +1, then it's useful, and otherwise it's not. And so you see that this is really kind of close to 0. It's somewhere around here. So that's not very useful at all. And so these movies we would say are really not very correlated. Now let's try movies 3 and 5. There's another example. So we'll go through again and we'll see 3 and 5. Now A works, so we'll just do next to it, we'll say check mark. We can use A because A has rated movie 3 and he's rated movie 5. We can use B again because B is rated movie 3, movie 5. We can't use 3 because this is part of the test set. Sorry, it's not part of the test set. This is value that we don't know. We can use user D right here because we know both these values. We cannot use E because we don't know this is part of the test set, and we cannot use F because this is part of the test set. But we do have 3 values now, 1, 2, 3 on each of these sides. So we have to do a little more. There's a little more terms here. So now we do this the same as last time. It's just we have 3 terms that we're summing instead of just 2. So we do this times this plus this times this plus this times this. So we have -1 times -0.43 plus 0.25 times -0.10 plus 0.25 again times -0.10. They actually turn out to be the same for both of those. Then we divide by the square roots of this squared plus this squared plus this squared times the square root of this squared plus this squared plus this squared. So we do the square root of 1 squared plus 0.25 squared plus 0.25 squared times the square root of 0.43 squared. Notice I'm omitting the square root, and that's because when you square something, it becomes positive again, so I don't need to write the square roots. Plus 0.1 squared plus 0.1 squared. And we do this. If you do this whole thing out, this entire multiplication, I'll leave it to you to actually run through the calculation, but you get 0.79 right here. And so that's closer to +1, right? So it's a positive correlation, and it's kind of close to +1. So we would say that these movies are positively correlated, right? So now we can use this and we can come up with a full table of similarity values. And here I'm tabulating this. This is similarity between 1 and 2. You can see the similarities between also 3 and 5, 0.79 we just found, and so on. And now a couple of things to note. First is that this table is symmetric, right? So we've said before that things sometimes aren't symmetric, but here they are. So the similarity from 1 to 2 is the same as the similarity from 2 to 1. So that's why 1 and 2 and 2 and 1 are the same. Just like take 2 and 4, for instance, and 4 and 2, same. So you can flop it over this, and or if you mirror image it over, it would be the same. Now in the next segment, we're going to choose one neighbor or movie, right? So we're having the neighbors be movies here. For each movie, we're going to choose one neighbor. And we could choose more. We could choose 2, 3, or 4, but we've already made the math complicated enough, and that would get even more complicated. So we'll just stick to choosing one neighbor for each movie, which will simplify things a lot when we actually go to do it out. And so basically down the columns right now, we'll say movie 1, we want to try to find the neighbor with the highest similarity, right? And so that's that would be 3 here, right? And these are all of the backgrounds now of green, which are the similarities, or the ones with the high similarities. So 1 would choose 3 as his neighbor for that reason. And again, remember, we're finding the magnitude, so we want the magnitude to be the highest. So even though this is negative, very negative, it's still really negatively correlated, which is a useful thing. And now for 2, we're going to choose 1. We choose between 0.11, 0.74, 1, and 0.88. And therefore, we're going to choose this. Even though, again, it's negative, it's still the highest in magnitude. For 3 would choose 1 because it's got negative 0.82, which is higher than any other values in magnitude. 4 would choose 2, just like 2 chose 4. Those are actually perfectly negative correlations with one another. So 4 and 2. And The reason that they're actually perfectly negative correlation is because there's only one value that we're multiplying here. And so that's not really that great. I mean, normally you need more data before you could say that two things are perfectly negative correlation, but here that's just the way it turns out. Now 5 will actually choose 2 to be his neighbor, right? Because 0.88 is higher than any other values. Now notice that 2 did not choose 5. 2 chose 4, but 5 chose 2. So they don't have to choose each other. Even though the table is symmetric, they don't necessarily choose each other. And we could define other metrics. For instance, we could say, all right, well, I'm not going to use similarity at all unless the similarity value is higher than like 0.9, for instance. And then in that case, we would only use one neighbor for one pair. Here, we wouldn't use similarity at all. Some people do that because sometimes it makes sense to say, well, unless the similarity is high enough, I'm not going to use it. But here we're just going to choose the most similar and just use that to do our calculation.